What's up? Here it is, another math video, a 2-for-1 special. This one on solving log equations and exponential equations. We're going to spend a day on each in class, but for the sake of the video, just figured I'd put them both in one video. So, first, some important properties to remember. Starting from the top, if you have two numbers with exponents, and it's the same base, you could, and they're set equal to each other, you could just set the exponents equal to each other. So we may get equations like that. That's a good property to know. Same thing with logs. If we have the log of x equals the log of y, and the bases are the same, then x must equal y. And these inverse properties will also help us solve. So if we look at this top one, or towards the bottom, a to the log of x base a equals x. The log of a base x, this part right here, is the number you raise a to get x. So if you raise a to that number, it makes sense that it's x. And then over here, if we were to put that in exponential form, a is your base, a to the x power is your answer, and then x is your exponent, we get a true statement. Alright? So that will help us solve logarithmic equations. So we're either going to rewrite one or both sides of the equation so that they're in the same form, and then use the one-to-one properties that we saw on the top of this page, or, oops, went back too many times, or we're going to, for exponential equations, we're going to isolate the exponential expression and then apply an inverse property. So remember, those were towards the bottom. Or we're going to isolate the logarithmic expression and apply an inverse property. So here's our first one. We're going to start off easy. E to the x power equals 72. The exponential part of the expression, the exponential expression is e to the x. It's already isolated. So now, what I like to do is think about when you isolate the exponential expression, put it into log form. So e would be your base, x would be your exponent, and then 72 is your answer. So in log form, we have bacon and eggs, base, answer, exponent. So we put that into that form, we get the log of b, which is e, a is our answer, and then it equals x. So in other words, x equals the natural log of 72. And that's it. We're done. So to actually figure out what that is, we would just type that into a calculator. So let's see, I still have my calculator open from last time. So we'll just do the natural log of 72. Alright, and we get 4.27. And that should make sense. We could check our work by raising e to that power. So e, where's this exponent button? Here we go, exponent. Alright, I found it. It was right here, x to the y power. I think it was 4.27, so if we go e to the 4.3 power, as a check, we should get something pretty close to 72. Alright, so let us try another one. So we got now one where the exponent is not isolated, so we have to isolate it. So we're going to do sad mep, poor little mep. Whenever we isolate a variable, we're going to do reverse PEMDAS when we try to isolate the variable. So that means add or subtract first. So we're going to add and subtract 4 to both sides. Okay, so that gives us 2 in parentheses 3 to the 2x minus 5 power equals 15. Then we're going to divide both sides by 2. So we get 3 to the 2x minus 5 power equals 7.5. Now we're going to put this into log form. So remember, our base was 3, our exponent was 2x minus 5, and our answer is 7.5. So now we're going to get, this is the log of 7.5 base 3 is equal to 2x minus 5. Alright, now our final answer as an exact number would be if we add 5 to both sides first. So we get the log of 7.5 base 3. We have to do that operation first, so the plus 5 would go outside of that, equals 2x, and then divide both sides by 2. Alright, so our exact answer for x would be right here. And if we wanted to evaluate that on a calculator, on a TI Inspire, you would just type that in. On any other type of calculator, we have to do the change of base formula, which would be the log of 7.5 over the log of 3, and then add 5 and then divide 2. So we could check that again on our calculator. So it would be the log of 7.5 base 3. So on our calculator, that would be the log of 7.5. See what that equals. And then divide by the log of 3. And then, actually, you completely forgot the other numbers were. I think it was plus 5 and then divide by 2. Yeah, so then you add 5 and then divide by 2. So this number, if you plugged it back into the original equation, if you plug 3.4 back into this original equation, it should give you an answer that works. Alright, let's try another one. So e to the 2x minus 3e to the x plus 2 equals 0. So this is a quadratic exponential equation. So if you notice, you have two exponential expressions and one exponent is double the other, then you want to treat this like a quadratic. So e to the 2x is really like e to the x squared, and then minus 3 times e to the x plus 2, and it's already set equal to 0, which means now we could just factor it. So you look for two numbers that multiply to 2 and add to negative 3. So we could rewrite this as e to the x minus 2 and e to the x minus 1 equals 0. Now we set both of these expressions equal to 0, and we get e to the x equals 2 and e to the x equals 1. So putting both of these into exponential form, we get x is equal to the log of 2 and x is equal to the log of 1. Alright, if it said, just without a calculator, tell me what x equals, that's the best you could do. If it said approximate to 2 or 3 decimal places, this is what you'd type in your calculator. Alright, and we know that this right here is going to equal 0 because the log of any base of 1 is going to be 0 because anything to the 0 power is 1. The other ln of 2 you would need a calculator to solve. Alright, and then here is a different type of exponential equation. That's if you have multiple exponential expressions and the bases are different and there's nothing else going on, like in this one, as opposed to the previous one where we had two exponential expressions but there was a plus 2 there and a times negative 3. If you have different bases, then what you could do is rewrite both of them with the same base. So these are both powers of 5, so you can rewrite 25 as 5 squared. So we rewrite 25 to the x plus 3 power as 5 squared to the x plus 3 power equals 5 cubed, because that's 125 to the 3x minus 2 power. So this is a power of a power right here and a power of a power right here. So we're going to multiply. So we have to make sure we distribute. So this becomes 5 to the 2x plus 6 power and equals 5 to the 9x minus 6 power. Alright, so now that both bases are the same, we could just set the exponents equal. So we get 2x plus 6 equals 9x minus 6. So that becomes 12 is equal to 7x. So x is about 12 over 7. Okay? Cool. Let's see what else we got here. Alright, now let's just do some logarithmic equations. So I made this in the same video because if you could solve an exponential equation, the log equations are the same steps, just when you get to the part where you isolated the log expression, now we're going to put it into exponential form, as opposed to when you isolate the exponential expression, put it into log form. So here, the log expression is isolated, right? The natural log of x equals 2. So remember, the natural log is the same thing as the log of x base e, alright? Which means now, base answer exponent, right? B-A-E, bacon and eggs, bay, however you want to remember it, that helps us put this into exponential form. So e would be our base, 2 would be our exponent, and x is our answer. Alright, so e squared is what you would take the natural log of to get 2. And you can actually check this with a calculator because this is one of the properties. If you take the log of a number with an exponent and that log has the same base as the base of the exponent, it's going to cancel out and you just get 2. Alright, so e squared is the answer. Here, ow, just ripped my arm, that really hurt. Alright, I'll make it. Tough it out. Bloopers. Alright, anyway. So we have two log expressions and nothing else going on. So I'll show you what to do when you have multiple log expressions and non-log expressions. In the next example. But if you just have a log expression should equal to another log expression and their bases are the same, alright, so that's important or else you wouldn't be able to do this. You could just set what's inside the logs equal because of the one-to-one property. So that's it. If that's the case, if you just have log expression equals log expression, just set what's inside the logs equal. Alright, so you can subtract x on both sides and add 1 on both sides, and then you get x equal to 2. Alright, and it should make sense because if you plug 2 in here, you get 9, and if you plug 2 in here, you get 9. And you can actually check this without a calculator because the log of 9 base 3 is 2, and the log of 9 base 3 is again 2. So that checks out. X equals 2 is our answer because it makes both sides of the equation equal 2. Alright, now like I said, what if we had multiple log expressions, okay, and like another term? Alright, what do we do? Oh my god, what do we do? I have no idea. Alright, sorry, I'm getting carried away. It's okay. It's okay. What we're going to do is use log properties. So rewrite this entire side. So if you have more than one log expression, group them together on one side of the equation like it's already been done in this problem. And then, so if the log of x minus 2 base 10 was on the other side, first thing I would do is subtract it over to the left side. Now we could rewrite this as one log expression because you're adding the log of 5x base 10 to the log of x minus 1 base 10. You could condense that to multiplication. So this becomes the log of 5x times x minus 1 base 10 equals 2. Alright? Now we're going to put this in exponential form. Base, answer, exponent. So 10 squared is equal to 5x times x minus 1, which if we distribute that, that'd be 5x squared minus 5x. Alright? Now we have 100 equals 5x squared minus 5x. Alright, I'm going to divide everything by 5 to make life easier. So we get 20 equals x squared minus x. Now it's a quadratic as it was in the previous step. So what I could have done was just bring everything over to one side. So I get 0 equals x squared minus x minus 20. And then I could factor that as x minus 5 times x plus 4. And I get x equals 5 and x equals negative 4. And we should double check that that works because logs have restricted domains. So we might get a number, because quadratics sometimes gives us extraneous solutions, we might get a number that would be a domain restriction. So like 5 works because if you plug 5 in, okay, you would get the log of 25 base 10 plus the log of 4 base 10. And that does happen to equal 2 because when you condense that, that's the log of 100 base 10. And we know that does equal 2. So that works. Alright, but if we plugged in, so that's good. Let me just change the color here, but red, we'll say red's bad. If we plugged in negative 4, we would get the log of negative 20 base 10 plus the log of negative 5 base 10, which doesn't work because if you do the log of negative 20 base 10, you get undefined, you get a domain restriction. But we got that extraneous solution because if you ignore that and apply the property of addition goes to multiplication, then we do get something that works, but it's still not a solution because of this domain restriction over here. You can't just ignore that. So negative 4 doesn't work, so just always check your work. And without a calculator, the best you could do is just see if there's a domain restriction. And so we get x is equal to 5. Alright, and I believe that's it. So thank you for watching 2 videos in one night. I'll be a better person for it, trust me. And that's it. Have a good night.